Yeah, geez, thanks for coming, guys. This is a better turnout than I hoped for. Okay, so I'm going to be talking about computing by collapsing, which is measurement-based quantum computing. So this is a very, I think, kind of miraculous paradigm for computation. If you know anything about normal computation in quantum mechanics, this is not at all like that. What we're doing here is we're measuring qubits only, and that constitutes the entirety of our algorithm, which is really surprising. So before I get going, I have a couple of inspirations for this talk, because this is actually not my specialization at all. My main inspiration is this absolutely delightful, whimsical diagram and dodo-filled book by Cook and Kissinger from Oxford, called Picturing Quantum Processes. I highly recommend that. If you're interested in anything I talk about, that's my first resource that you should check out. But the talk itself is mainly based on this paper, also by Kissinger, but this time with John van Wetering. And yeah, the talk is kind of an overview of that paper. If you're interested in the string diagrams that I speak about, then this paper shows how they also apply to other fields like logic, computation, and actually also linguistics. So this is quite general. Okay, so before I dive into the meat of the talk, because this is an undergrad talk, I do need to talk a little bit about how quantum computing usually works. So in quantum computing, you have a state, which is the current state of whatever it is that you're computing with. That can be like an electron, in which case the state would be, say, its spin. The important thing is that the state is discretized to two main levels.
Just stand a bit more
okay.
on the screen. Yeah.
The state is discretized to two main levels, and the general state is described as a superposition of those two levels. So the levels in this case are the two basis vectors 1, 0, and 0, 1, which we think of as representing a computational 1 or a computational 0. But the general state, it has some complex numbers that scale each of those two states. So it's a number in C2. The gates in our computation, so like logic gates in classical computation, are now 2 by 2 unitary matrices. Unitary meaning that their conjugate transpose is equal to the matrix itself. And here are a couple of examples. So these are all quite important gates, X, Z, and H, and we'll see them again later in the talk. But other than that, we'll see them again later. It's not so important that you understand what they do per se. The next thing to understand is how computing with multiple qubits works. So this is one of the interesting features about quantum mechanics. If I have 2 qubits, I describe it with 4 numbers instead of just 2. If I have 3 qubits, it becomes 8 numbers. 4 qubits, it becomes 16, and so on. There's an exponential growth in the amount of information as qubits increase. And that's because the state of the n-qubit system is described actually by a tensor power of C2. And the gates then are tensor products of gates acting on each of the individual qubits. Here are 2 gates that we'll also encounter later, CZ and CX. Once again, aside from the fact that we'll encounter them later, it's not so important that you understand what they do if you don't already. I realize that not everyone knows what tensor products are. So because I've taken all this effort to avoid bracket notation, because it's not something that undergrads encounter, let me introduce tensor products as an operation on matrices. So when I say the tensor product of 2 columns, you should just take the second column and multiply it into the first component-wise, like that. And then the same thing is for matrices as well, right? And what this means is that when the tensor product of 2 matrices acts on the tensor product of 2 states, it acts component-wise. The first matrix acting on the first state, second matrix on the second state, and so on. Okay. Now, an aspect of quantum computing is how we get information out. And the way that we do that is with measurement. Now, there are a couple of things that is important for you to understand about measurement, because obviously my entire paradigm is about measurement, so I'm going to spend a little bit of time on this slide. The first thing you need to know is when we make a measurement, we always get a bit, a classical bit. So, at least for the kind of measurement I'm describing. So we get either 0 or 1. That's our outcome set. But we can make that measurement with respect to different bases. And these bases are described by basis vectors for C2. They're also, as it turns out, eigenbases for certain matrices. So that is the basis of eigenvectors of a matrix. So this basis up here is the eigenvectors of the Z matrix, and this one is the eigenvectors of the X matrix. But for our purposes, it's just important to know that they are different, and we can pick one of them when we're making a measurement, and that will influence the outcome that we get in a way that I'll describe in just a moment. And usually when we measure with respect to the Z basis, we talk about measuring Z. And when we measure with respect to the X basis, we talk about measuring X. But this is a bit of an abuse of terminology. Okay, so how do our outcomes work? Well, basically we have our state, we choose a basis, and the outcome that we get is determined by how that vector is expressed with respect to that basis. So you express your vector with respect to that basis, and you get a 0 alpha squared of the time, and you get a 1 beta squared of the time. And the other important thing about this, aside from the fact that it's non-deterministic, is that it collapses your state, it destroys it. After the measurement, depending on what you got, the state becomes the corresponding basis vector. Okay, so let's phrase this a bit more generally, more mathematically. So this operation of collapsing our state down to one of these basis vectors is a projection, and we can write it as a projection operator, normalized. Don't worry about the normalization. Actually, I'm not going to worry about normalizations at all throughout the rest of the talk. And the probability is expressed as well in terms of that projector. And obviously, all of this generalizes to n qubits. To make measurements on n qubits, it's just basically single qubit measurements, but tensor products with a bunch of identities. Last thing you need to know, before we talk about the real meat of the talk, is traditionally a quantum algorithm, by virtue of gates being unitaries, a quantum algorithm involves you prepare a state, you apply a unitary transformation to that state, a unitary matrix, and in general, it can be any unitary matrix. Any unitary matrix you like is a valid quantum operation, and then you'd make some measurements to get results out the other side. So then a natural question is, there are infinitely many unitary matrices, right? So how can I possibly do all quantum computations? And the answer is, we pick what's called a universal set of gates. Now, this is universal in the sense that any unitary transformation can be approximated to arbitrary accuracy using just these three, H, C, Z, and T. So I'm about to introduce a new paradigm for quantum computation, and I want to convince you that it's universal. So in order to do that, in order to convince you that I can do any quantum computing calculation, I just need to convince you that I can do these three. Okay, cool. With all that, let's start talking about MBQC. So the idea here is, like I alluded to, the entire computation consists of measurement. So what that means is that we're going to start by preparing a state ahead of time, and that state that we prepare is going to be independent of the computation that we're actually doing. It's called a resource state. It's independent of the algorithm. And then our algorithm, the entire algorithm, is going to consist of making a bunch of single qubit measurements on this resource state. And somehow we're supposed to get a deterministic result out of this, right? At least some of the time, because there exists some deterministic quantum algorithms. So the algorithm comprises, to be more specific, a choice of, for each qubit, the order of the qubit measurements, so I can measure one qubit before the other, or vice versa, and the basis for each. And that is all the control that I have. From that and that alone, I have to be able to produce any result. So the question naturally becomes, each of these measurements is destructive, and in particular non-deterministic. How on earth am I supposed to compose these in order to get actual computation, actual useful computation? Is it even possible? And surprisingly, the answer is yes. And the central idea here is going to be something called feed-forward. Now, basically, this just means that I'm going to base my order and my basis for future measurements upon the results that I obtain from prior measurements. And I can do that in any classical way. So I can use that information, I can perform some function on that information, classical function, mind you, and that's going to dictate what I do for future measurements, right? So there's more freedom maybe than it seems at first. Okay, so let's dive into the specifics. The first specific is, how is this resource state prepared? What does it look like, right? Because I said that it's independent of algorithm, but I at least need to tell you how to construct one that's good enough for all algorithms, right? So let's talk about how we represent resource states. This is the gate that we're going to use to entangle our qubits. It's called the parity phase gate. It's dependent on this parameter alpha. We're only ever going to use alpha equals pi over 2 and pi over 4. Our resource state we're going to draw as a graph. The vertices of the graph are going to be qubits, or represent qubits, and they're all initially going to be prepared in the same state, x0, or plus if you know Dirac notation. Then we're going to repeatedly apply the parity phase gate to pairs, either once or twice. One application with alpha equals pi over 4 will give us some amount of entanglement between those two qubits. It'll change the state in some way that we represent visually as drawing a line between those two qubits. If we do that twice, it turns out that p pi over 4 squared is just p pi over 2. So doing it twice, we draw with 2 lines, representing that we've applied that gate twice to those qubits. And any more than that doesn't give us anything new or useful, at least not up to local transformations. So this is what the resource state will be drawn as. I guess the only thing that's important to say here is that the order in which we do these entanglements doesn't matter. The gate commutes with applications to other qubits. So the graph is all that remains, the unordered representation. Okay, so then what's an algorithm? Okay, so for an algorithm, we want to now take this graph and we're going to label every vertex with a measurement expression. So this measurement expression is going to encode where we store the result and how we determine the basis. Right, so what is all of this? So the AIs represent outcomes. In particular, the AIs appearing as arguments to the function phi are the previous outcomes. Phi is some classical function that will compute, and the result of that function will tell us whether or not to measure an x or z basis. I should mention all of these variables are between 0 and 1. In particular, phi also returns 0 or 1. So here's an example labeling. You can see the vertices down here are labeled with constants, but they are allowed to depend on others. So D over here depends on the value of A, E depends on the values of B and C. Now, how do we actually execute this algorithm, or rather, what does it represent? So what we're going to do is for each qubit, ignore the first thing for now, for each qubit, we're going to either measure x or z. We're going to measure x whenever our function is 0, we're going to measure z otherwise. And then we're going to store the result in a(n plus 1). The only thing worth mentioning is that we first have to sort these measurements in a way that all of the dependencies are resolved, right? So that if, for instance, the basis of measurement for qubit E depends on that of B and C, we can only measure it after we've measured B and C. But otherwise, the order is flexible. Okay, is everyone following at this point? Any questions? So that's what I meant about topologically sorting our dependencies, sorting them in order of dependence, and then measuring them in that order. And this is an algorithm, so this is all of the algorithms will be drawn in this way. The next thing we might want to ask is, I said I want to convince you that we can build a universal gate set. So what is a gate? We need some way of composing diagrams, right? Composing these algorithms. And that way is given to us by pattern fragments. And here's where it gets a little bit tricky to explain, not to understand, but I'm going to do my best. So a pattern fragment is like an ordinary pattern with two major exceptions. Firstly, it has inputs, and secondly, it has outputs. So the inputs are just some subset of the vertices that we choose, and we call these inputs. And the outputs are likewise a subset of the vertices, and they're labeled accordingly. Inputs are labeled with an expression like this. Don't worry about what it means just yet. Outputs are labeled with an expression like this. The key feature is inputs are allowed to start in any state, not just x0. Right? When we were preparing this state, our assumption was that all of the qubits started in the state x0. But if we're thinking about a fragment now, we assume that our input can start in any other state as determined by what happened before. Right? And the outputs we leave unmeasured by the end of applying the fragment. So we measure all the other qubits, we don't measure the outputs. So what are these x's and the xi's? Well, because the measurements are non-deterministic, we need a bookkeeping device for keeping track of potential errors. And it turns out that the device is given to us by this machinery. So we assume that our incoming state, V, can be V up to potential application of either x or z. I say potential application, x to the power of x, little x here is a binary value, 0 or 1. So if it's 0, then we don't apply x, and if it's 1, then we do apply x, and likewise for little z. So our incoming state could have these potential leading, we call them Pauli errors. Now, what we require in order for this gate fragment to implement a gate G is that the outgoing state should be G times V, the application of the gate G on V, modulo or up to some potential Pauli errors outgoing. And what we need to be able to do is keep track of how those errors depend on the incoming ones and on the results that we got, so that we know what's leading. Okay. So in particular, psi and zeta are going to be functions of all of the measurement outcomes and potentially also the incoming errors. So let's look at an example. Here's an example. So here, psi is d plus z. Z is one of the incoming errors, d is one of the measurement outcomes. And this one is x, so it just depends on the incoming error. I'm not at all suggesting that this is a useful pattern, by the way. This is just a complete example. But you can see this green vertex corresponds to an input, that red one corresponds to an output. We can have more than one input, more than one output. They don't necessarily have to be disjoint. Okay. Any questions at this point?
Can you just say the first part again when you jumped to D, X, and D? You just did that very fast. You said D plus D.
Oh, yes. Yeah. So I was saying that psi, which is our outgoing X error, which is, remember, either 0 or 1, is in this case dependent on D and Z. In this case, the dependency is through XOR, which I've written here as plus. I should probably have clarified that. So it's addition modulo 2, if you will, right? Because obviously all of these values are binary values. These are particularly simple functions, right? Like this one is just the function x, but they could be in theory more complicated. Again, this is just an example. Okay. I suppose one other thing worthy of mentioning is that these Pauli errors commute with each other. So we don't need to worry about the order necessarily of them, just that they're there. Or, yeah, anyway. Okay. So my claim, I hope everyone is following up to this point because this is the formalism that we're going to be working in. My claim is that this formalism is universal. So in order to do this, I have to exhibit a pattern fragment for H. There it is. Looks like a monster, but it's not really that bad. And my claim is that for an incoming state, V, up to some Pauli errors, the outgoing state, which is going to be that one, will be H times V up to some precomposition with Pauli errors. Likewise, here's a pattern fragment for T. Oh, something worthy of note for H. There is no feed forward here. None of my measurement bases depend on any of the prior ones, right? This one is a 0, so I'm going to measure it in the X basis. This one's a 1, so I'm going to measure it in the Z basis. There's no feed forward, but there is in T up there. And likewise, CZ has no feed forward. So the only one that actually requires feed forward is T, which is kind of interesting, and there are good reasons for that that I'm not going to have time to talk about. Okay. So, let's prove this. But before I can prove it, I have to introduce you to ZX calculus, which is honestly one of my main motivations for this talk, because this is just truly beautiful. So, ZX calculus is two things. Firstly, it's a notation. Secondly, it's a set of rewriting rules for that notation. So the notation, first of all. The notation is comprised of wires and then two primitives called spiders. So meet the spiders. There's the Z spider and there's the X spider. I'll also probably call them the black and white spider sometimes. Now, they each have a phase associated with them and they have a certain number of inputs and outputs. So these represent linear maps between some number of vectors and some number of vectors, right? So linear maps between tensor power of C2 and some other tensor power of C2. Now, in general, these are obviously not going to be unitary. In particular, the number of inputs can differ from the number of outputs, but we can compose them to get unitary gates. So they will eventually describe our system. And there they are written in terms of the vectors. So we have a direct translation into ZX calculus. Now, it's worthy of stressing, I guess, at this point that it's not necessary to translate it into matrices. It's actually possible and done in the Picturing Quantum Processes book that I plugged at the beginning to formulate all of quantum mechanics entirely in terms of diagrams like this with no reference at all to matrices. This is entirely to help us understand what these things do. Do you have a question?
Just clarification.
Yeah.
Can you raise one of the states to power with the tensor?
Yeah.
Is that just tensor product itself?
Yes. Yes.
Okay.
Yes. So that's going to be enormous. If like as a vector, that's going to be a very long vector if m is non-trivial, right? Yeah. So these are often more convenient than using the vector notation, but I mean, we could actually change to a slightly better notation anyway, but we'll see the benefit of this in a second. Now, these guys compose in two ways. We can compose them horizontally. Now, what that means is you take one of them and you stick its outputs adjacent to the inputs of the other and connect them. And that represents composing the two linear maps as linear maps. Or we can compose them vertically, which basically just means take some spider, say this, and put it on top of some other spider. But don't connect anything. And what that corresponds to is taking the tensor product of those two linear maps. Right? Okay. So let's see how this notation can recover what we've already seen. Firstly, we want to recover states. So states in this notation are just one-legged spiders of the opposite color. So the Z states are the X one-legged spiders, or the black one-legged spiders, and the X states are the Z one-legged spiders. B here is a binary number as usual, with either phase pi or 0. If you know anything about this, this should be familiar. I am ignoring constants, but basically what I'm saying is that Z, 0, or let me rather do X. X0, which you might also know as this, is this spider, which is equal to so I've written it in both there. I've written it in both notations in case you know the rough notation. And there are some normalizations that we're not worrying about for the sake of this. Likewise, we can get gates. So B is binary. That means that this is either the identity or Z, and it's just the Z spider, two-legged. This is either the identity or X. It's just the two-legged spider with X. We're going to need a notation for the Hadamard gate, which we met earlier, but we can actually write that in terms of the others. So we're going to use this little notation for a square, but it just translates into that. And finally, we're going to want to derive what CZ looks like. So you can convince yourself, and I'm not doing this calculation here, that these two spiders composed in this way gives you CZ, or sorry, CX. But remarkably, you can compose them in the opposite direction as well. So here we think of first doing this linear map, then doing this linear map. Here we think of doing them in the opposite order, but they give us the same thing. They both give us CX. And so we can write this without ambiguity like that, which is a weird and suggestive notation, right? Because now what we've lost is a sense of time flowing from left to right. We've just got vertically stacked nodes, and this is going to be a recurring theme, and we'll see why in just a second. Okay, so that's the notation. How do we manipulate them with the calculus? So meet the dance of the spiders. Now, there's a bunch of rules here, and honestly, it's kind of hard to parse them and remember them, so I'll do my best to talk over them when I use them. But the first one is spiders confuse. When spiders are connected, they can do a little dance and fuse into a single spider with their phases added. This is the pi commutation rule. It means when you move a pi past the spider of the other color, you pick up a minus sign. The copy rule means that if you have a one-legged spider attached to a spider of another color, it destroys the other color and copies itself in its place. And then a few more rules. Exchange, when you have a complete subgraph, you can delete it and turn it into two nodes. When you move a Hadamard past the spider, you can change the color of the spider. Two Hadamards cancel. Any two-legged spider with no phase cancels. And that's all the rules. I appreciate that there's a few of them, but again, I'll try reference them when I use them. Now, a couple of noteworthy things. These two rules together imply color inversions of all the others. So, in particular, black spiders confuse too. Not just white ones, but I've just drawn only some of them because we can invert all of them. Like just swap the colors for any one of these. And secondly, I claim that only topology matters. What I mean by that is that we don't actually care about how these spiders are ordered when they're connected to each other. We can move them around freely. We only care about their connectivity. And that's a bit of a bold claim, so I just want to spend a little bit of time talking about what makes that possible. So, in our context, what makes that possible is what some of you might know as the Bell state or the Bell effect. I'm going to call them cups and caps. This is a cup. It's a two-legged spider where both are facing in the same direction, which looks a little bit weird, but it corresponds to the state. It's a perfectly legitimate state, perfectly legitimate vector. This is a cap, also a perfectly legitimate vector. What makes these two interesting is that when we put them together, they satisfy what I've called the Yankin identity, which is, you can imagine sort of straightening that piece of string out. But really, it's just spider fusion, right? Because here we have an invisible spider, here we have an invisible spider, and they can fuse together to give us another invisible spider down at the bottom, right? Okay. But what makes these things remarkable is we can use the cups and caps to convert inputs to outputs and outputs to inputs. This is sometimes called the process state duality. So this dodo represents any diagram you like, right? And what I claim is that I can bend one of the outputs back into an input. And I can turn this diagram, which had no inputs and two outputs, into one which has one input and one output. processes become states, and states become processes. These are not necessarily representing, the same linear map. They're not at all the same linear map, but I can freely convert between them, is the key point. And likewise, in the opposite direction. And if I do first this map and then this map, I get back to the identity because of the yanking.
How do we know with the first image on the right? How do we know that it's now one input and one output?
I'm imagining that we're reading left to right still.
Okay.
Yeah.
So, but not where the line enters the diagram.
Yes, no, it's almost as if time flows backwards there. It's a little bit hard to parse, but we shouldn't think of it as time flowing backwards. If we wanted to understand that diagram, what we should do is decompose it into smaller diagrams and look at each of them in part, right? So if we could if we wanted to compute that diagram, suppose that the box represented some function f, right? We could do it in parts. Here we have an identity. Here we have f tensor identity. I guess this is actually identity tensor identity. Here we have our state, and here we have an identity, right? Like what I'm saying is you can break these things up to read it left to right, but you shouldn't think necessarily of. There's like a logical flow to the diagram that's different from how it's actually calculated, right? Okay. The other thing that we can do with these cups and caps is we can define a rotated version of our diagram. We can attach a cup there, a cap there, and then define this rotation to be that, so as if we pulled the wires taut again, right? And actually, there's a bunch of symmetries that we can do. And this is called the transpose. There's a bunch of symmetries we can do. We can Hermitian conjugate, that flips our diagram. And in this case, it also makes all the phases negative, which I've indicated with the little star. And you can check that just on the matrix level. Then we can transpose, which corresponds to rotating. So if we do one after the other, we should get another operation, which is the conjugate. And of course, I can complete the diagram with the rest of it. Now, what I'm not claiming is that all of these are the same linear map. They're not, right? What I am claiming is that we can freely convert between these different pictures. So any calculation that we do at this level, we could likewise do at this level and then convert back when we're done. Okay. And the reason that we have these operations, by the way, is because the space, or the category, if you will, of finite dimensional Hilbert spaces forms what's called a dagger compact closed category. The compact closed is what gives us the cups and caps. The dagger gives us the dagger. But anyway, that's not the entire picture, but I'm not going to say more about that really in this talk, but if you're interested. More importantly, for our purposes, cups and caps can change spider legs from outputs to inputs, can bend spider legs. And what's relevant here is that a spider with a bent leg is still a spider. It's not some new mysterious linear map, it's just another spider. And again, this is actually just spider fusion, right? Because again, we have an invisible spider here that just fused with that one. The cross-hatching here indicates either color. So this is what lets us reorder spiders when they're connected. Why? Well, because suppose we have two spiders connected in, say, this order. I can introduce, cup, cap, cup over here, cancels with cap over here, so I've done nothing. But this is now a spider with a bent leg. And this is a spider with a bent leg, so it turns into that. And here presto, I've reordered it.
So,
yes.
How is the left different from the right, where you've reordered it?
Well, they're not. That's the whole point. They're not different. The answer is the same, and it's because of this cup and cap transformation, and because the spiders with bent legs are still spiders, where we just swap from inputs to outputs. So my whole point is that whenever we're composing, I've drawn two-legged spiders here. They could have had any number of legs. Whenever we're drawing spiders that are interconnected, we can put them in any order. That's my whole point. Okay. Yes.
Is the node that's on the right on the left now the one that's on the left on the right? If that makes sense.
What?
So is the
No. So they've switched. So this is maybe color that maybe.
No.
Okay. All right. And actually, I've been a little bit disingenuous because now I'm reading plan upwards. I should probably have kept it horizontal. I'm sorry. I'm sorry about that. Yes. It's force of habit because it's actually how it's often done. Yeah.
Okay, just to clarify, time is
this direction and the...
No, time is horizontal for the presentation. I just screwed up. Yeah, time is vertical, yeah.
The white one went from receiving input to giving output.
Yes, yeah. Here white was getting an input from black. Here white is giving an output to black. Okay. So the next thing that we might want to ask is, how powerful is this stuff, right? Like, what can we do in it? And it turns out it's very powerful. Every quantum state, every quantum gate, well, pure state, and every projective measurement can be expressed in this notation. And in fact, this notation is a strict superset of the usual circuit notation that some of you might know. Usually we write quantum algorithms as circuit diagrams, and this is a complete superset of that. So not every ZX diagram is a circuit, but every circuit is a ZX diagram. And also, every manipulation that we do with the diagrams corresponds to a valid manipulation on their respective matrices. That's called soundness. And, and likewise, every manipulation that we do on the level of matrices corresponds to a valid manipulation on the level of diagrams. That's called completeness. So it's very powerful. It's just as powerful as circuits and more. Okay, with all that said, let's finally use this to look at measurement-based quantum computing. So the first thing that we want to do is express our parity phase gate in this notation, because that was the key to building our entangled states. So this is a small calculation. Right here, I'm just looking on the level of matrices. I identify this matrix as just conjugated with CX this matrix. I then identify this matrix as a tensor product of these two, because this one, if I take it into each of the components here, gives me one of these subblocks, 2 by 2. And then finally, what I've got out on this side is something I know how to write in ZX calculus, because I've established how to write CX. There's this guy. And I've established, obviously, this guy is just this one, the two-legged Z spider, and it's tensored with the identity, and tensoring means stacking. So there's our parity phase gate, but it's not a very good notation for the parity phase gate for reasons that we'll see later. So it's helpful to first massage it a little bit into a different form. And this means that we have an excuse to do our first calculation in the calculus. So let's go. Now, this is going to happen a bit fast. So coming up is the next axiom I'm going to invoke. That axiom is color-coded to correspond to vertices. I hope you can see the colors up there, but I'll also flick backwards and forwards to show you a little bit. So what's about to happen is the top 2 white spiders are going to fuse, and the bottom white spider is going to unfuse. Let's watch that happen. Happening. Top 2 fused, bottom 1 unfused.
So the one labeled alpha, if that turned into 2
Alpha
spiders.
turned into 2 smaller spiders, these 2. Okay. Coming up, we have another fusion, except this time it's just unfusion. All 3 of these nodes are going to unfuse. They're unfused. Right. Now we're going to rearrange this. So we're going to take this node and drag it over to the left here, and that's going to twist our diagram up a little bit, like that. Now we identify a complete subgraph over there. We're going to collapse that down into 2 nodes using the exchange rule. And now finally, we ditch our identities at the bottom. Nodes by themselves are just the identity. Okay, so we get this. And this is a much more convenient form for what we're going to do for reasons that we'll see in just a second. Okay, so we have our parity phase gate. How do we do the rest of our pattern fragments? It's actually remarkably straightforward. So vertices are all starting at x0, and x0 is just a one-legged spider, a one-legged white spider. We established this earlier. So all of our vertices we replace with these one-legged spiders. Then all of our edges correspond to application of the parity phase gate on some vertices. So we just associate the vertices with the ends of the parity phase gate, slap that boy on there, and hey, presto, right? Now, in particular, obviously, we choose alpha pi over 4 for single vertices or single edges, and alpha pi over 2 for double edges. Correspond to a projection, which in particular involves an application of a dual basis. So a dagger, if you had like x0, then a measurement would apply x0 dagger. Now we learned earlier that the dagger is just a horizontal reflection. So all of those states that we derived, if we want to get their daggers, we just reflect them. Now these measurements attach to these ends here. Not necessarily in this exact order. This is just an example to show you where they attach. And finally, our errors are x to the x and z to the z. Well, we learned how to represent that earlier. It's just like that. So we're going to attach that to our input. And we're going to leave in particular our input, we're going to leave a dangling wire on the input and a dangling wire on the output. Look at this in practice. Is everyone with me so far? Really? Did I lose you somewhere?
Well, I mean, this is the thing.
Okay, yeah?
Could you clarify again, what you mean by errors? Is that like a...
So the errors are the incoming state and the outgoing state have to differ by application of the gate that we're trying to implement, but they can also potentially have an application of X or Z on them, just because of the non-determinism of the measurements. So the errors, when I talk about errors, I talk about us tracking whether an X or a Z is applied through the process of applying our gate. And we represented them by application of X to the X, Z to the Z, where X and Z are Boolean. Okay. Let's just actually watch this happen. So here's the thing that I claimed was the H fragment. Let's expand it out. I've replaced all the vertices with white vertices in a suggestive manner. So now let's first of all make our input and our output wire. There they are. I'm going to drop the incoming errors just for the time being. We'll put them back in at the end. Next, I'm going to attach the measurements over here. So this function is a constant function of 0, which means we should measure in the X basis, which means we should attach a white spider. Our white spider. Here we want to attach a black spider because we're measuring in Z basis. We attach all the other spiders correspondingly. Now focus your attention on this edge over here. It represents application of p pi over 4, which remember was that little weird virus-looking thing that we derived. So we stick that weird virus-looking thing there. Similarly, for this double edge, it was an application of p pi over 2, so we put that there. Do that to the remaining edges. And we've converted our fragment. Now the claim is that this represents H, and we're going to now use ZX calculus to reduce it to just H. So we have the same thing as before, except now more complicated. So these two are going to fuse, those two are going to fuse, these two are going to fuse. We're going to use the copy rule here, which means that this black node is going to delete that white one and copy itself once. So just basically delete it and replace it. So watch that happen. Right, now we're going to fuse these two and we're going to copy, but here it's actually a copy because there are two outputs here, so this guy's going to copy himself twice. In particular, one's attached here and one's attached here. So watch that happen. Okay. Now these little guys over here are dangling, they're just constants. We throw those away because we're not worried about constants if they're non-zero. We're going to move this pi past that pi over 2, and we're going to have to pick up a minus sign because of the pi commutation. In particular, we're going to have to pick up -1 to the power of d, because we don't know if d is 0 or 1. And moving it past there basically just means moving it off. It's going to disappear. So when we do that, we get here. As promised, there's a -1 to the d. And we fuse the top spiders. Now here, we're going to fuse these and then unfuse them in a different order. So we're going to fuse them in the order C pi plus this, and we're going to unfuse them in this order. This is just a trick to do with modular 2 arithmetic. Those two things are equal mod 2. And then over here, we're going to turn this into a black node by introducing a Hadamard gate next to it, and we're going to write that Hadamard gate out in full. So doing that, it looks a lot more complicated, but it really isn't. These middle two have now unfused into these. And over here, we've turned these guys black and introduced the Hadamard. Okay. Last mile. We're getting there, and I'm not going to do all of them, don't worry. So we're going to fuse these guys, it's going to turn into a black spider. We're going to move that black spider onto here using the copy rule. It's going to delete this white node, and we're going to fuse these two. And same thing underneath. That simplifies the diagram a heck of a lot. Finally, we fuse. And now we're basically done. At this point, we just need to move all of these errors, the things that depend on our measurement outcomes, up to the top to collect them together in the outgoing errors. And when we do that, every time we move it past something, we're going to invoke the pi commutation rule, where we pick up a minus sign to the power of that thing that we moved past. Then we're going to rewrite it in modular 2 arithmetic, just like we did earlier. And I'm going to skip all of the details here because it's boring, and we've seen it happen at least once. So when we do that, this is what happens. What we're left with down here, you probably, hopefully, recognize as a Hadamard. That's how we defined it. What we have up here is outgoing errors. I haven't accounted for the incoming errors yet, but they just moved past the Hadamard. They changed their color because Hadamards change color, and they go join their friends up there. So when we include those, that's what we get. And it worked. Okay, that was a lot. So I'm just going to gloss over the other ones. Here we have feed forward, so we actually need to attach a vertex there that depends on the previous outcomes. So the easiest way to do this is just to consider cases. It's not the only way. You can write it actually strictly in ZX notation, but you could just consider cases. So this converts to this, simplifies to that, which is indeed application of t followed by some errors. Cx or Cz, sorry, was this, converts to this, converts to this. Now there's no feed forward again, so everything's simple. And then this simplifies down to that, which is indeed Cz, followed by some errors. We haven't derived the form of Cz.
The application of errors. So what you're saying is we can apply Cz, and then depending on our measurement outcomes, we just apply X or Z so many times.
Well, we can't actually apply X or Z because we don't have X or Z. But what actually happens is we push those errors all the way to the end of our calculation. We do our final measurement, and then because we know that there is an X error or that there is a Z error, we can adjust for the probabilities that we get. I hope that makes sense. So we actually never remove the errors. We just push them all the way through our calculation, all the way to the end. And then our final measurement will just have its probabilities adjusted according to the presence of an error. Okay, so like that is it. That is my talk basically. The last things I wanted to say were that there exist really good tools for automating this. Here's one. It's called PyZX. And this is quite cool because it actually uses the ZX calculus as like a primitive for its intermediate compilation. And then there's likewise one that's a bit more visual called Quantumatic. But that's it. So in terms of references, I actually just wanted to go back to the beginning of the talk to stress that if you're interested in any of this stuff, you should check out, my goodness, so many slides. You should check out these, at least one of these. So this introduces all of quantum mechanics in terms of pictures. These pictures are a subset of the pictures they introduced. This is the paper that's actually to do with what I spoke about. So if you want to follow up on the details of the talk, specifically MBQC, then this paper is the one to go to. And this one by Bayes is a lovely demonstration of how the math behind these diagrams, the category theory, applies to other fields very well as well. But otherwise, that's the talk. I'll take any remaining questions.
Yeah.
So the paper I reviewed was in 2019, but the math of the category theory is much older than that. I'm not actually entirely sure when these string diagrams started to become popular. I know that they were, I know Bruce would know a lot more actually about this, I'm sure. I know that they were after category theory was introduced by quite a large margin, because they rely on something called a monoidal category, which is a category with a certain enriched structure. Anyway, I'm digressing a little bit, but the point is, recently, but not that recently. I don't know exactly when.
In physics, back to Penrose. Back to Penrose, where you discovered this diagram of notations.
There you go.
And then the mathematicians took it up in the 90s.
Right.
Yeah, and you can use similar notation for indice calculations, where you have, like in general relativity, where you have to keep track of a lot of indices. You can represent the type of the indices with boxes that connect together with wires in this way, where the wires now represent index contraction. Anyone who's done relativity will probably understand what I'm talking about, but the calculations have counterparts in other areas of physics that are not necessarily ZX calculus. I think those go back to Penrose, right?
Yeah, both of them.
Right.
The same root,
Right.
Penrose.
Any other questions?
I mean, yeah, I didn't really understand. So I understand the ZX calculus, so
Yeah.
good. I didn't understand the measurement-based quantum computation.
Yeah.
So I would like you just to do the simplest algorithm just on the board.
The simplest algorithm on the board.
Yeah.
I mean, none of them are particularly simple because all of the.
Let's take that one. So just explain mechanically. I've got a box.
Okay.
And I do this, and I do that.
So what you would do here is, so each of these represent a qubit. Yeah.
Okay.
Each of the vertices.
Yeah, but I want you to be very specific. I walk into a room and I
Yes.
do what?
Okay. So you walk into a room, you collect 5 qubits, right? Then you prepare your resource state, which involves taking those qubits and entangling them pairwise with application of P alpha. Those are the double edges there. That preparation will be independent of the algorithm that you're producing. So actually, this is a point that I didn't quite explain. I showed you fragments for the 3 gates. I didn't show you how to connect them. there is a connection of all of them that is universal, in the sense that you can do any sequence of the gates then as well. I left that out of the talk because I didn't think I'd have time, but that means that there is a single resource state that you prepare for any quantum algorithm that you could possibly conceive of doing. In this particular case, let's suppose it's the simple 5-qubit one. It isn't, it's a lot more than that, but suppose it was. Well, then you'd walk in here, and you would measure this guy in the x basis, and you'd store whatever result you get, you'd store in A, your variable A. Then you would measure this guy in the z basis, whatever result you get, store in B.
So, well, 1 second then, what is the, how come you, when you say that, I understand what you're saying, but I don't understand what 0 arrow A, but you're saying that the first thing you do is you measure that guy on the bottom left, that qubit, in the x basis.
Yes, x basis because the function on the right-hand side of the arrow is 0.
Okay.
It evaluates to 0, which means we measure it in the x basis. We then store the result that we get the outcome of that measurement. We store it in the variable A.
Okay, let's carry on.
So then you would measure this guy in the z basis and store
Well,
it.
how do I know to measure it in the z basis?
Because now the right-hand side of the arrow is 1, which corresponds to measuring in the z basis.
Okay.
Then you would store the result in B.
Okay.
Then you would measure this guy in the z basis as well. Store the result in C. Measure this guy in a basis that's dependent on what you got for A. So if you got a 0, you would measure him in the x basis. If you got a 1, you'd measure him in the z basis.
Okay.
And then likewise measure the final qubits in a basis dependent on B and C. So if B XOR C is 0, you measure yeah.
Okay, 1 second. So then, and the final output is going to be either 0 or 1. Then. Like, okay.
Yes.
Yeah, am I right?
Yes.
So this is an algorithm which you're taking 5 qubits. You walk into a room, you prepare 5 qubits. You do some measurements, and in the end, you get either a 0 or a 1.
In this case, yes. Yeah, and you would repeat the experiment, like say 100 times. You get some distribution of either 0 or 1. That distribution would be the result of your quantum calculation. This is a single qubit example, but in a more complicated case, you would end up having, let's say, 7 or 8 output nodes, and then you'd measure each of those, and that 7 or 8, that vector of length 7 or 8 of 1s or 0s would be your outcome. And you'd get a distribution over those. And this is very similar to what you currently do with quantum computing, right? You prepare, let's say, 8 qubits in some initial state. You run it through a circuit, you do some measurements, what you get is 8 1s or 0s.
What is exactly different?
What is different is that we're not directly applying any unitaries, at least not part of the algorithm. The algorithm doesn't involve any application of quantum gates. And that means that we could pre-prepare the resource state. I could hand it to you on a little circuit, and like it's been pre-prepared by someone else in another room across the world. Then your algorithm just involves measuring it.
Yeah, and measurements is like sort of simpler.
Well, not only is it simpler, so there's actually a lot of reasons why it's nice. One of the reasons is, in some cases, you can do measurements simultaneously. Like here, we could measure all 3 of these at the same time. So it's vastly parallelizable in that sense. And the only time it's ever not parallelizable is when there's feed-forward involved. And in the gates that I showed, in the actual eventual universal gates I showed, the only one that involved feed-forward was this T. So you only actually need to worry about feeding your results forward at each of the points where T enters into your algorithm. Everywhere else, you can do everything in parallel. In a certain sense, I don't know if you know the Gottes-Munn-Mill theorem, but basically the Gottes-Munn-Mill theorem is if we restrict ourselves to Pauli quantum mechanics, so just Pauli, Clifford, so the Pauli gates and everything they generate, all algorithms can be efficiently classically simulated. So where all of the inability to classically simulate comes from is actually the P alpha pi over 4. If that makes any sense. It's the single edges of our graph where all of the non-simulability comes from. So when we're doing a computation like this, we can do vast swaths of it either on a simulator or actually on quantum circuitry, but in parallel, and then just worry about the quantum bits when we actually get to those single gate feed-forward bits of the calculation, if that makes any sense. I'm probably not doing great justice to this. It's more in the paper on exactly why we care about this formalism in that regard. Yeah.
For each vertex corresponding to some state, the basis at which we measure is calculated by a classical algorithm, right?
And actually a really simple one, because I mean, if you look at, like, here's the classical algorithm here's a classical function that determines whether I measure E in the X or the Z basis. And all it depends on is the XOR of two other bits. It's an incredibly simple classical function. It's not like we're having to go off and do something incredibly computationally expensive. It's a simple combination of the previous outcomes. Yeah.
How does this compare in like the number of qubits you need to do the computation versus?
I think it's more. I'm not actually certain. Well, no, it would be more. Like, it's definitely more, because if I want to do an 8-qubit computation in traditional quantum mechanics, I prepare 8 qubits. That's it. And then I need a way of applying gates to them, and that way introduces noise, because it's going to be something like hit them with pulses of light of exactly the right duration to like flip their Bloch vector by a corresponding angle on the Bloch sphere. But it's a noisy operation that you're doing on, but just 8 qubits. Here, the trade-off is we have many more qubits. To do any operation of any magnitude, you need a lot of qubits. But all of the gate application happens ahead of time, and thereafter there's nothing that introduces any more noise. At that point, it's just measurement. I mean, measurement does introduce a noise, but I think, actually, I can't speak for the current state of our technology. But anyway, it's a different paradigm. I don't actually know whether measurement introduces more or less noise in our current devices than application of gates, but it's certainly at least different. So traditionally, you would only prepare 8 gates and then you only measure those. I mean, 8 states, and you'd only measure those. Yeah?
In the other version, you apply gates and that introduces noise, but in this version, you prepare states. Is there also noise that gets introduced there, or that's the errors that you're talking about?
Yeah, no, those are not the errors. No, the errors are just a product of the fact that the measurement itself is non-deterministic. We can't hope to implement a deterministic gate without having to account for the possibility that some of our measurements don't give us the answers that we want. And that's what those errors are there for. They keep track of how the output of the gate differs from what we want it to be by application of X or Z. But that's not as a result of the state being badly prepared. That's a theoretical thing. That's not a practical thing. But there will be some practical noise as well. But the same is true of any quantum computation, right? If I take a state that was initially prepared in 0 or Z0, and then I apply a Hadamard to it and I measure it in the X basis, in theory I should get 100% of the time 0, but you don't, obviously, right? Likewise, in this case, you're also going to have some classical uncertainty associated because we don't know exactly how we've prepared the states. Okay, I said that all of pure state quantum mechanics can be formulated in this. If you want to account for classical uncertainty, you need mixed states. Where did I say that now? Later. If you want to account for classical uncertainty, you also need mixed states. And I think that you can also formulate them in this notation, but I don't know how. I think there's an extension of ZX calculus that works fine for non-pure states, but I don't know how that works. Anyway. So you could build like a calculation of classical uncertainty into your model, I think, is what I'm saying. I believe I've seen it, but I can't tell you details. Yeah.
So if one of the advantages of this method is avoiding the noise of planned gates by having pre-prepared states.
Yeah, so if what you're asking, do we not get as much noise in pre-preparing the state? To be perfectly honest, I think that the answer to that will be very dependent on how the gate is applied in practice.
I think one of the advantages as well is time constraints. It takes time to apply those different gates. And with this, you don't need, like if you want to do a complex operation, you need a long string of gates sometimes. You need a long string, and that takes time to implement. With this, it's very fast.
Yeah, that's what I was saying. When you actually do the calculation, you can do a large portion of it in parallel. You're not applying gates, you're just measuring. But yeah, thank you. That's a good point. But like, as far as the noise introduced goes, I'm sure that there would be noise introduced as well. It seems as though there might be more noise because there's more applications of pairwise entanglements. But I think in practice, it depends a lot on your actual hardware. Like on what are your qubits? Are they electrons? Are they circuits? Are they whatever else? Super cooled something or another. I'm not very clued up on quantum hardware.
At
But
the moment, that is kind of what they're working on now is measurement-based quantum computing has a lot of advantages, and they are trying to make it experimentally viable.
right.
More, well, more easily applicable than the current quantum systems that we use.
I think one thing that is cool about it is that the actual execution of the algorithm is physically a lot simpler than the construction of the resource state, in the sense that you could do away with less hardware to just do the measurements than you would need potentially to actually prepare it. So those two things could happen in different places, which is nice. And like you say, you move all the computationally expensive stuff to the preparation, which happens beforehand elsewhere. Anyway, I think I'm about out of time. Thank you.